All right, well, it's test week here, so we're going to get you ready for that today. The test opens today, closes on Wednesday, and we'll cover up through Chapter 20. So last time we were talking about regioselectivity of electrophilic aromatic substitution reactions when you already have a group on the benzene ring. And I said that, for example, if you've got nitrobenzene and you do the chlorination reaction, you see exclusively the meta product, whereas if you have aniline, you see exclusively the ortho and para products and none of the meta product. And we were about to rationalize that when class ended last time. So I hope you've had a chance to look at the intermediate that you get from meta substitution. This is the carbocationic non-aromatic high energy intermediate that forms when the electrophile attaches at the metacarbon. I'm not drawing those other resonance structures, but I want you to note that that positive charge could be delocalized by resonance on all of the pink places. You just move the double bond over, right? Now I want us to consider how the stability of that intermediate is relative to the intermediate where, say, chloro would be on the ortho carbon. All right, so let's draw that intermediate. Here again is the nitro group. We'll put the chloro on the ortho carbon. That would put a positive charge here. And of course, by resonance, that positive charge could be delocalized in those three places. So you've got this meta intermediate and the ortho intermediate. We could also draw the para intermediate, and maybe that would be worth doing. It's not that difficult. So here's the nitro group. Here's the chloro on the para carbon with the positive charge here. And you can see that for the para intermediate, the positive charge is likewise on the same three carbons as it is with the ortho intermediate. So there's a clue why ortho and para always go together, because their intermediates put positive charge on the exact same carbons. Now, looking at stability, which do you think is better, the meta intermediate or the ortho and para intermediate? Meta. What is better about the meta versus the, or what is less good about ortho/para? Well, you see in the ortho and in the para, that plus charge is on the carbon that's directly adjacent to the electron withdrawing group, the one that has a positive formal charge on it, the one that is, by resonance, already sucking electron density out of the ring. So these two are less stable because they put the positive charge on the same carbon as the electron withdrawing group. So the meta intermediate is just less bad. It's still a high energy carbocationic intermediate, but it is it's the best option, and so that's the pathway that's preferred, okay? And that's why we get meta substitution when what we've got on the ring is an electron withdrawing group. In contrast, you can do the same thing with the aniline. I should just copy and paste, but for those of you that are writing on paper and can't, we'll just draw things out. So let's draw the meta intermediate for the aniline. That would put the chloro here, the plus charge here, nitrogen there. And this would tend to put the positive charge on these three carbons, just as we saw above for the meta intermediate. Sure. I mean, I just drew a different resonance structure, I guess, than I did above. Huh. I want to keep things consistent. It's fine. So the positive charge can be on those 3 carbons. That's the meta intermediate. Let's draw the ortho intermediate. And you can see that in the ortho intermediate, and then over to our right, we will also draw the para intermediate. You'll see that in both cases for ortho and para substitution, we're going to end up putting the positive charge adjacent to the amino group, where lone pairs from the amino group can actually donate in to make a new pi bond, and we get access to this additional resonance structure where the positive charge from the ring is now out on the nitrogen. We can draw one of these. I won't do it because we don't have space, but we can draw one of these for the para intermediate as well. So the ortho intermediate and the para intermediate are going to be more stable because they are more resonance stabilized with the electron donating group. And that is why for electron donating groups, we prefer ortho and para intermediates, because in that intermediate, the plus charge is on, at least partially on the carbon that's adjacent to the donating group, and that donating group can stabilize the positive charge, either by resonance or by an inductive effect, okay? So we will see that donating groups are ortho and para directors, and withdrawing groups tend to be meta directors. So what counts as a donating group? For regioselectivity purposes, here are your electron donating groups, roughly in order of donating ability. So for example, the line and the squiggly line means attached to the benzene ring. An NH2 group, or maybe even a primary amine or a secondary amine, where R is like alkyl. These are strong electron donating groups by resonance. A little bit lower is the OH or OR, OH or ethers. The reason that amines are better donors than ethers is because nitrogen is less electronegative than oxygen, so nitrogen's more willing to share its electron density than oxygen. Also on this list would be amides. An amide is where the nitrogen on the ring is adjacent to a carbonyl. And then a little bit lower than that would be esters, where the nitrogen that's directly attached to the ring is also adjacent to a carbonyl. Why do you suppose the amide is lower down the list than the amine? What's the difference there? That adjacent carbonyl is attenuating or decreasing the availability of the lone pair to donate into the benzene ring, because now these lone pairs can go this way out onto the carbonyl oxygen. Now, some of you have learned, if you've been reading your text, that carbonyls, when directly attached to the ring, are electron withdrawing groups. This amide is not an electron withdrawing group because the carbonyl is not directly attached to the ring, it's the nitrogen. So you got to pay attention to which atom. You can't just memorize carbonyls are electron withdrawing groups, you got to pay attention to which atom is attached to the benzene ring. If it's an atom with a heteroatom with a lone pair on it, that's going to be an electron donating group via resonance. Also, here are alkyl groups. So CH3 or branching or tertiary. These, of course, are electron donating groups, but not by resonance because they don't have lone pairs. There's a couple of ways that this is explained, why they are donating groups. Some people explain it in terms of an inductive effect. The rationale here is that an sp3 hybridized carbon is less electronegative than an sp2 hybridized carbon, meaning the sp2 hybridized carbon can actually pull electron density away from the sp3 carbon. And so sp3 carbons donate electron density into the ring just through an electronegativity effect. There's some controversy over that. There continue to be papers published doing calculations that suggest that this effect is not actually that important, and that perhaps a bigger effect is hyperconjugation. So you have seen before that a filled carbon-hydrogen bonding orbital can line up with an empty orbital and donate electron density into it. So let's just imagine we're doing an electrophilic aromatic substitution reaction. What's likely happening in that ortho or para intermediate is you're putting a positive charge, which corresponds to an empty orbital, on the carbon where the methyl group is, and those CH bonds are donating electron density into the ring via hyperconjugation. You could think of this as some sort of sigma to pi star type of hyperconjugation. We don't need to go in any more detail than that, and it's fine to just memorize that alkyl groups are electron donating groups. Last on our list are the halides, Cl and Br and F. These are all, I know I put them on the wrong side, I'm sorry. These are all electron donating groups by resonance because you've got lone pairs on the atom adjacent to the ring. And so they can stabilize the positively charged intermediate, okay? These count as electron donating groups as far as regioselectivity is concerned. They are electron donating groups by resonance, and they are ortho and para directors accordingly. But in terms of nucleophilicity, they are electron withdrawing groups due to electronegativity. And in fact, they make the corresponding aryl halide less reactive than benzene. So students, I've noticed in the past, get somewhat confused about the halides. Are they donating groups or withdrawing groups? And the answer is yes, and it depends what you're talking about, which is, of course, the most frustrating answer. They are donating groups when it comes to ortho and para directors. They will direct substitution to be ortho and para because of the lone pair on the heteroatom that can stabilize the positively charged intermediate by resonance. But if you want to talk about, is a chlorobenzene more or less reactive than benzene as a nucleophile, it's less, because the electronegativity dominates for that particular effect. Okay? So then we have the electron withdrawing groups, and we won't list these in any particular order. We won't list these in necessarily, I'm going to try to list them as well as I know, but I may not know. So anyway, ketones, aldehydes, are electron withdrawing groups by resonance, and they follow the pattern of the atom attached to the ring is pi bonded to an electronegative atom, and you can draw a resonance structure in which the oxygen is negatively charged and the carbonyl carbon is positively charged. So you should be able to see how that would withdraw electron density away from the ring. Similarly, for similar reasons, the sulfonic acid group and the nitro group are electron withdrawing groups by resonance. You can probably rank carbonyl compounds in terms of their ability to withdraw electron density based on what you already know from earlier this semester with their reactivity. For example, you know that aldehydes and ketones are more reactive, that is more electron poor than esters. So you would predict that the ketone would be a better electron withdrawing group than the ester. Notice the difference between what I just drew here and what I drew there. It's different depending on how you attach to the benzene ring, via the oxygen, in which case it's a donating group, or via the carbonyl carbon, in which case it's a withdrawing group. All right. Questions about that? In terms of regioselectivity, these donating groups are ortho and para directors for the reasons we've talked about. The electron withdrawing groups are meta directors for the reasons that we've talked about. Yeah?
Can you just say again why the ester would be better than the ketone, or why the ketone would be a better withdrawing group than the ester?
Yeah, so you're going to use what you already know in terms of carbonyl compound reactivity to predict how well of a donate or withdrawing group it is. Ketones and aldehydes are more reactive than esters. They're more electrophilic. There's a bigger plus on the carbonyl carbon. Esters are less, in part because the ester oxygen acts as an electron donating group, donating electron density into the carbonyl carbon. Okay, good. Others? All right. So with all of that in mind, we're now prepared to do some synthesis questions. Some of these are easy, some of them are more difficult. All right, so here is a benzene ring with an amide. And we're going to do a Friedel-Crafts reaction, and it looks like it's a Friedel-Crafts acylation. All right, so first thing you got to do is decide the group that's already on the ring. What kind of group is it? So you tell me, what kind of group is that? That is an electron donating group by resonance. Accordingly, it is an ortho and para director. So I'll use color blue to highlight the ortho and para positions. So you predict that the next reaction is going to put the acyl group on the ortho carbon or the para carbon, but not the metacarbon. Okay? And so that would be on a predict the products question, those are the two products. In a synthesis question, you can use whichever you need, or either the ortho or the para, and assume that you can separate them easily. Okay. This is a decent time to talk about some limitations to the Friedel-Crafts reaction, because it turns out that if you already have a strong electron withdrawing group on the ring, that is a resonance electron withdrawing group, and you attempt to do the Friedel-Crafts reaction, it turns out you don't get anything. And the answer, and the reason why is the benzene ring is too electron poor to be a good enough nucleophile for the Friedel-Crafts reaction. So that's one limitation of the Friedel-Crafts reaction, and that can influence in a synthesis the order of the order in which you do things. Okay. Another problematic issue with the Friedel-Crafts reaction is, what if I wanted to use the aniline to do the same basic reaction? And the answer there is it doesn't work either. Not for the same reason, though. That aniline is a good electron donating group via resonance, so you predict that this is a good enough nucleophile. The problem is that the lone pair on the nitrogen is reactive enough to attack the Lewis acid catalyst. And as that catalyst is essential, you end up getting an intermediate that looks like this, where the aluminum is bound to the nitrogen of the aniline. And you're sort of stuck there. So Friedel-Crafts reactions don't work well with anilines either. The workaround to that is but you notice that if you put the carbonyl on the nitrogen, if you convert that aniline into an amide, then the reaction works fine. The explanation for that is the adjacent carbonyl is delocalizing the nitrogen lone pairs and making them less reactive, so they don't interfere with the Lewis acid catalyst there, and you can go ahead and do the reaction. So if your goal were to make a molecule where you did the Friedel-Crafts reaction on the aniline ring, first you would want to modify the nitrogen with the acyl group, do the Friedel-Crafts reaction, and then after the fact, you could do the amide hydrolysis reaction, which we learned about briefly in chapter 16. You use acid and water, and you can hydrolyze an amide back to that ketone product. And your text will do that a couple of times. And so you'll see that in some of the practice problems that you'll do, using sort of thinking strategically about the limitations of various reactions, making some decisions about where to put things. Okay, yes?
What are the reagents we use to take the aniline to the amide?
Amide, so if you wanted to sidestep and make the amide, it turns out that you could do either with acetic acid and DCC, that's sort of carboxylic acid coupling conditions, or you could just use the corresponding acid chloride. And that's nucleophilic acyl substitution chemistry from chapter 16. All right. We could spend more time practicing, is this an ortho-para director and where is it going to go? But I think that comes pretty easy. What we want to do now is what happens when things are more complicated, and then we want to practice synthesis. So let's look at what happens when you already have two groups on the benzene ring. So let's start out with this one, a nitro group and an OH group. We don't yet know how to put OH groups on benzene rings. We're going to learn that in the next chapter, but we don't know it yet, so don't worry about, well, I'm not sure how I would make this molecule from benzene. You're not expected to at this stage. Let's do a subsequent halogenation. Oops. So we got to decide the groups on the ring, are they ortho and para directors or are they meta directors? So Here is a donating group. OH is an electron donating group by resonance. It's an ortho and para director. Nitro is a withdrawing group. It is a meta director. So we have to identify positions that are meta to the nitrogen. Meta to the nitro group, that would be here. We can't, of course, put anything else there. Do you see how we couldn't do an electrophilic aromatic substitution on the carbon that has the OH group? Do you remember that in the intermediate, the carbon that gets the electrophile gets deprotonated? So if there's not a proton on a carbon, you can't do electrophilic aromatic substitution there. Okay, how about the OH group? Which places does it prefer? Ortho and para. So you've got some disagreement here. And whenever you're in a disagreement, whenever two groups oppose each other's regioselectivity, the rule that your text says is the strongest donor wins. Okay? And in part, the reason donors prevail over withdrawers is, remember that with the withdrawing preference is related to the fact that the ortho and para intermediates put a positive charge adjacent to the ring, whereas the meta-intermediate doesn't. The meta-intermediate doesn't stabilize the positive charge, it just destabilizes it less. For the donating groups, though, ortho and para stabilizes the positive charge by donation of those electrons. So donating groups generally overcome the withdrawing ability of withdrawing groups. So you'll just simply choose to put the next group on one of the blue carbons because the strongest donor is going to win. Now, this example is nice because aside from identifying the blue carbons where we're going to put the group, it allows us to state another limitation for these reactions, and generally that is this. If two groups are already meta to each other, sterics block the middle ortho position. So we're going to rule out this blue carbon here because it's in between two groups that are meta to each other, and sterics make that reaction difficult to do. So we'll choose to put bromo here and then also on the other carbon, on the other blue carbon. Those would be the two products. We would see none of the substitution product where the bromo was here, and none where the bromo was on the orange carbon, and none where the bromo was on the blue carbon. All right? Does that make sense? Follow that? All right, let's do just a couple more. Here we have an aldehyde and an alkyl group, and let's do the nitration reaction. Again, it's useful to remember that the alkyl group is an electron donating group, so it's an ortho and para director. The aldehyde is an electron withdrawing group, so it's a meta director. Here are the carbons that are ortho and para to the electron donating group. Here are the carbons that are meta to the electron withdrawing group. Here we see agreement, right? That's a great situation. That's easy. So the two products we would get are where the new nitro group goes on either this carbon or this carbon. We don't see any of the other options where the nitro group is on the carbons that are ortho and para to the aldehyde. Now, some of you are going to look at that and say, what the heck, you just told us not to do that. And the answer is, I didn't tell you not to do that, you just memorized it wrong, okay? Remember, if two groups are already meta to each other, we don't substitute at the position, the middle ortho position that's in between them. How is that different from this situation? Two groups were ortho to each other. Do you see how this carbon where we put the nitro group isn't sterically hindered because it's not between two groups? Yeah. So the rule is not you can never have three things in a row. The rule is that if two groups are meta to each other, you can't do the middle ortho position. Two groups are ortho to each other, you can for sure do on the sides. Okay. With all of that, I mean, oh, sure, let's do this one. This one's fun. Fun. Sorry about my voice today. I don't know what's wrong. I think it's low. Maybe you're like, your voice is always annoying, Bryce, so whatever. Yeah. All right, so we'll do the sulfonation reaction. This installs a sulfonic acid. Here you've got two donating groups. This one, both of them are electron donating groups by resonance. We'll just color them differently so we can examine their regioselective preferences differently. The methoxy group is an ortho and para director, so is the bromo group. Here are the ortho and para positions relative to methoxy. Oh, that's boring. Boring is fine. Here are the ortho para positions relative to bromo. So that's lovely because their regioselective preferences reinforce and there's no controversy at all. So then we would not do this one in between the two metagroups, but we would do this one. And then the other option where the sulfonic acid is there. What I wanted to do, what I was hoping to do and didn't get to do was, what if two donating groups oppose each other? So maybe just briefly, we'll do one more example, methyl and methoxy, and we'll do the chlorination reaction. Methoxy prefers ortho and para to itself. Methyl prefers ortho and para to itself. Which is the strongest donating group? So this is where you want to have that order of groups, get some intuitive sense for which groups are better donating than others. In general, the resonance donating groups, with the exception of the bromo and the chloro, all of the strong resonance donating groups are higher up on our list than the alkyl groups. So you would preferentially go with the methoxy group over the alkyl group, and you would choose to put the chloro ortho or para to the methoxy and not ortho and para to the alkyl group. Okay. All right, now, yeah, go ahead.
So are we going to have to know when they're both donating or both withdrawing, which one's stronger?
If they're both, the only rule I can get out of your text is the strongest donating group wins. So probably if you find a situation where two withdrawing groups oppose each other, there is probably a better way. But I don't think you'll be in that situation. Okay, others? Yeah.
How do we know if a donating group
How do you know if a donating group is stronger than a withdrawing group? You don't. The donor wins. Yep. Yeah, you don't have to rank donor groups versus withdrawing groups. The donor wins. Okay, so now we need to do some synthesis. And let's see. There we go. Some of this is going to require strategy. All of it's going to require strategy, and in most of these cases, the order is going to be important. Okay, so we'll start out maybe a little bit easier and get more difficult. Okay, so you want to make this molecule, you want to have the nitrogen and the alkyl group be ortho to each other. And you want the bromo group to be at this meta position, or meta to the alkyl group, but para to the nitro. I'm sorry, para to the nitrogen. So when you start this process, it's good to keep track of a few things. First off, how are you going to make the bonds? And of course, the starting material is benzene. So I can make that through the bromination reaction. That's easy. I can make this bond through the Friedel-Crafts alkylation. And then the aniline, how do I do that? I don't have a way to do it directly. What's my strategy there? Do nitration first and then reduction afterwards with hydrogen and palladium on carbon, right? The next thing to do is to think about the relationship between the two groups. So we can get between various groups on the ring, so we can get a sense for what had to have happened first. All right. Aniline is ortho to the alkyl group. Aniline is para to the bromo group. That checks out. But bromo is meta to the alkyl group. Once you've done that, now summarize the abilities of each of these groups. They are all actually electron donating groups. So one part of the puzzle we're going to have to solve is how do you get the bromo meta to this donating group? All right. Another thing we're going to need to do is look for potential conflicts. For example, we're going to remember that the Friedel-Crafts reaction doesn't work well. Doesn't work well with anilines. And the other thing is it doesn't work well with nitro groups. For the anilines, the problem is the lone pair on the nitrogen's too reactive. For nitro groups, the problem is the benzene ring itself is not reactive enough. So that gives us a hint as to what we want to do first. We can't do the Friedel-Crafts reaction after the aniline's there. We can't do it if the nitro's there, so our best shot is to do it first. Okay. So now let's just start. So we've got an idea. Let's do the Friedel-Crafts reaction first. Okay, so I'm going to just propose an idea. why don't we take that 3-carbon alkyl halide and aluminum chloride and then do that. So far, so good. Then what do I do? Go ahead. Okay, could you turn it into a carbonyl? How? Okay. You wanna, if you did KMNO4, we could clip off this bond and make that a carboxylic acid. Though in the end, we do want those 3 carbons to be there. So I think you're thinking, well, if I had a withdrawing group, I could get the bromo on the right carbon, right? Okay, that's good. What about, so let's run with that. Let's actually put it in as a withdrawing group first, knowing that later we have chemistry that gets rid of that ketone. We learned that. That's ketone reduction with hydrazine. That's one of the 2 ways we learned to get rid of ketones later on. All right, so let's install it first as an electron withdrawing group. Then, what do I want to do next? Do I want to put the nitro on first, or do I want to put the bromo group on first? Let's go ahead with bromo, because the nitrogen ends up needing to be ortho to this, right? And right now, that's an electron withdrawing group, which is a meta director. So, let's put the bromo on, and that will go on the meta position. All right, good. Now at this stage, I could proceed with doing the nitro and hope that the bromo as a donating group would overwhelm the electron withdrawing capabilities of this. That's probably fine. For our purposes though, I think it's probably better to do the ketone reduction to an alkane that we learned about. You could either use zinc and mercury, or you could use hydrazine under basic conditions. That's gonna convert the alkyl chain to, the ketone to an alkyl chain. Now we're in a great situation because bromo favors ortho and para substitution, but so does the alkyl group. Their preferences reinforce each other. I'm only going to draw the desired product, which is the one where the nitro group happens here. Of course, we would get the other product, and we would assume that it was easy to separate the 2. You are allowed to do this for ortho and para substitution. You're not allowed to do this for ortho para versus meta. Do you see what I'm saying? I'm not drawing the other product, okay? And then to get to the final desired product, we're just going to do hydrogen and palladium on carbon. All right, questions about that strategy? This is not the same sort of you can do retrosynthesis in the same way that we've done it in the past, but the reactions here are fairly simple. It's pretty clear what the new bonds you had to form are. The trick is the order in which you do the reactions and whether you needed a ketone alkyl group switch or a nitro aniline switch to take care of the various reactions and the regioselectivity. Yeah?
Would it be possible to do the alkylation and the nitration and then the bromination?
So could you do the alkylation first, then the nitration, then the bromination? So what you're proposing, I'm just going to copy and paste for the sake of, you're proposing this reaction, and the issue is the donor group is going to win, and that donor group prefers substitution,
Well, if you reduce the...
here. Oh, okay. Okay, yeah, so you're proposing let's before we put the bromo on, let's go alkyl, then nitro, then aniline, then Br2. And there, the strongest donor wins. Yeah, I think that would work.
Would it not make that complex with iron?
Would it make apparently not. So you learned that anilines are a problem with aluminum. Your text doesn't say it's a problem with iron. So you're right to worry about it, but that's not a problem your text notes. So yeah, I think that's a good strategy. There's probably a reason why your text doesn't use this. There's another problem with anilines and halogenation. Anilines are reactive enough that often more than one halide goes on there. Your text has a workaround. I don't care enough to worry about it. So yeah, I would call this okay. Other alternatives? I mean, we got like 5 minutes left, so let's do one more. And then I'm going to recommend that you practice. I mean, duh, but yeah. And maybe we'll see how far we get on this. We may just have enough time to map out what we need to do. Okay. So first, how do we make the new bonds? Chloro, that's just the chlorination reaction. We can do this one through a Friedel-Crafts approach, either alkylation directly, or we can do acylation followed by reduction. We may need to do that if we need to take care of regioselectivity. This other one is a little bit more difficult. And here you may need to think backwards a little bit. As I said, we don't do Friedel-Crafts reactions with vinyl halides. So probably we need to think backwards a little bit. This could have been the benzyl bromide that we talked about, and we could have gotten that from just the alkyl group. And that we talked about in Friday's lecture, so if you need to go back and review that. But one strategy there would be Friedel-Crafts alkylation, then radical halogenation at the benzylic carbon, and then E2 elimination to get the alkene. Now let's take care of the spacing between the groups. These two are meta, these two are ortho, these two are para. So, at some point, we're going to need to either get the chloro meta to this group, or we'll need to have these two groups present and trust that one will be more powerful than the chloro. So you may find some different answers here. I like to choose a pathway, if possible, where the regioselectivity doesn't oppose itself. So here's my brief solution, and I'm not going to have time to draw intermediates, but I want you to work this out and see whether there's other options. I would do Friedel-Crafts acylation first, then I would do chlorination to put the group put the chloro meta to our alkyl group. Then I would do that hydrazine-based alkene carbonyl reduction. That turns these both into electron donating groups. They're both going to prefer the next carbon. Ooh, I just saw a problem with what I was going to do. Okay, scratch that. Dope. All right, well, we're out of time, and I know that scares you. What I will do is I'll write a solution. This is actually problem Which problem is it? This is problem 20.61 in your text, 20.61D. I'll write a solution, you can look at it, but there's a lot of synthesis problems in your text that you should practice. Anyway, good luck, I will see you next time.